Why do we use logarithmic differentiation? In calculus, when I want to find derivative of some function, I'll be taking natural logarithm on both sides and continue the derivative process. Why do I take natural logarithm on both sides for some function to get derivative? What's the reason behind it? That's what we are going to see in this video. Okay, here we have two cases. That is, in calculus, there are two cases where we use logarithmic differentiation to get derivative of a function. Okay, let's look at the first case. In the first case, we have the function y is equal to 3 to the x power. Here, we have variable x at the exponent. In a function, if you have variable at the exponent and you want to find derivative of such function, you must use logarithmic differentiation. That is, you have to take natural logarithm on both sides of this function and continue the derivative process. So it is a rule. So in a function, if you have variable at the exponent and you want to find derivative of such function, you must take natural logarithm on both sides and continue the derivative process and find dy over dx. Okay, let's look at the case 2. In case 2, we have a function that is y is equal to square root of 1 positive x over 1 negative x. Okay, here, if I want to find the derivative of this function, before I start finding derivative, I first write this square root as an exponent. Then I'll be getting 1 positive x over 1 negative x to the power 1 half. Okay, in the next step, I can find the derivative of this one with respect to x. So if I find derivative of this y with respect to x, I'll be getting dy over dx. So I have to use a power rule of derivative. That is, I have to bring this exponent 1 half in front of it. Then I'll be getting 1 half times 1 positive x over 1 negative x to the power 1 half negative 1. So I brought the exponent 1 half in front of the stuff what we have over here and subtract 1 from the exponent. So far I've done derivative only for the exponent 1 half. By chain rule, I have to do further derivative for this stuff. So here we have variable in both numerator and denominator. So I have to use quotient rule to get derivative of this one. Okay, so even when we talk about the quotient rule, it's very clear. It's a little lengthy process. So to make when I want to find derivative of such function, so first I find derivative for the exponent, and then by chain rule, when I find derivative for this one, I have to use quotient rule. So it takes a little lengthy process to get derivative. So to avoid this, to make the derivative process easier, what we need to do is we have to take natural logarithm on both sides and use the properties of logarithm. So what will happen if I take natural logarithm and use the properties of logarithm? So I'll be able to split up this stuff into parts. So when I split up this the particular stuff, square root of 1 positive x over 1 negative x into parts, the process of derivative will be easier. So this is the main reason. Case 2, this is the main reason why we use logarithmic differentiation, because even a complicated function can be split up into parts so that we can find the derivative of each part easily. Okay, now what we can do is we can look at the derivative of each of these two functions separately. Let's find the derivative of the function y is equal to 3 to the power x. As I told you already, we have variable at the exponent in this function. Okay, in a function, if I have variable at the exponent and I want to find derivative of such function, so what I need to do is I have to use logarithmic differentiation. That is, I have to take natural logarithm on both sides, then use the properties of logarithm. Finally, I have to find derivative. Okay, here, this is a rule I have to follow to find derivative of a function. So where I have variable at the exponent. Okay, in the first step, I'm going to take natural logarithm on both sides. When I do it so, I'll be getting ln y is equal to ln of 3 to the x power. Okay, here on the right side, I'm going to use the properties of logarithm. That is, I'm going to use the power rule of logarithm. So that is, I have to bring this exponent x in front of the logarithm. So then I'll be getting x times ln 3. Okay, now I can find the derivative on both sides with respect to x. Okay, when I find derivative on the left side, here for ln y, I have to do derivative for ln. So when I do derivative for ln, that is for natural logarithm, I have to put 1 in numerator, and whatever argument I have for the natural logarithm, that should be taken in denominator. So this is the derivative for natural logarithm. Okay, so far I have done derivative only for the natural logarithm. By chain rule, I have to do derivative for this y. So when I do derivative for this y with respect to x, it will be dy over dx. Okay, on the right side, we have variable x times ln 3. Already we know that 3 is a constant, and natural logarithm of a constant is also a constant. That is, this complete ln3 is a constant multiplied by the variable x. Okay, when I find derivative, if a variable is multiplied by a constant, I have to keep the constant as it is and find derivative of the variable alone. Okay, when I find derivative of this x with respect to x, it's just 1 times ln3. So I get 1 over y times dy over dx equals to 1 times ln3 is ln3. Okay, now my aim is to get dy over dx. That gives the differentiation of the given function with respect to x. So to solve for dy over dx, I have to get rid of this 1 over y. So to get rid of this 1 over y, I'm going to multiply both sides by y. So this y will cancel out. I get dy over dx equals to ln3 times y can be written as y times ln3. Okay, here the next step, this y can be replaced by 3 to the power x, because y and 3 to the power x are equal. So in this step, this y can be replaced by 3 to the power x. So dy over dx is equal to 3 to the power x times ln3. Okay, I got the derivative of the given function y is equal to 3 to the power x. That is dy over dx equal to 3 to the power x times ln3. Let's find the derivative of the function y is equal to square root of 1 positive x over 1 negative x. When I want to find derivative of this kind of complicated functions, what I can do is, as I told you, we can take natural logarithm on both sides, use the properties of logarithm, then we can find the derivative. When I take natural logarithm on both sides, I can use the properties of logarithm over here. So I'll be able to split up the function into parts. So once I split up the function into parts, I can find the derivative of each part easily. So now I'm going to take natural logarithm on both sides. So I'm getting ln y is equal to ln square root of 1 positive x over 1 negative x. So ln y equals to, the next step, what I'm going to do is, I'm going to write the square root as the exponent. Then I'll be getting 1 positive x over 1 negative x to the power 1 half. Whenever I write square root as exponent, it will be 1 half. Okay, ln y is equal to, here I'm going to use a power rule of logarithm. That is, I have to bring this exponent 1 half in front of this logarithm. Then I'll be getting 1 half times ln of 1 positive x over 1 negative x. Okay, here in the next step, I'm going to use a coefficient rule of logarithm, because in this logarithm, we have two quantities are in division. In the argument of logarithm, if two quantities are in division, we have to take logarithm for numerator and denominator separately, and I have to subtract them. That's a coefficient rule of logarithm. So then I'll be getting ln of 1 positive x negative ln of 1 negative x. Okay, so that's all. We can use the properties of logarithm. In the next step, we can find the derivative. So here in this step, I'm going to find derivative on both sides with respect to x. Okay, if I find derivative of this natural logarithm, I have to take 1 in numerator, and whatever argument I have for the logarithm, that should be taken in denominator. So far I have done only for this natural logarithm. By chain rule, I have to do further derivative for this y. When I find derivative of this y with respect to x, it will be dy over dx. Okay, here on the right side, we have constant 1 over 2, and it is multiplied by the variable part, because this part contains variable. So whenever a constant is multiplied by the variable and I want to find derivative, I have to keep the constant as it is, and I have to find the derivative of the variable part. So when I find derivative of this natural logarithm of 1 positive x, I have to take 1 in numerator divided by the argument of the logarithm should be taken in denominator. So I get 1 over 1 positive x. So far I have done derivative only for this natural logarithm. By chain rule, if I find derivative of this 1 positive x with respect to x, this 1 will become 0. The derivative of x with respect to x, it will become 1. So 0 positive 1 is just 1. Negative, the same thing. So when I find derivative of this natural logarithm of 1 negative x, it will be 1 over 1 negative x. So far I've done derivative only for the natural logarithm. By chain rule, when I find derivative for this 1 will become 0, and this negative x will become negative 1. So I'm getting the derivative of 1 negative x with respect to x is just negative 1. Okay, now 1 over y times dy over dx equals to 1 over 2 times 1 over 1 positive x times 1 will be 1 over 1 positive x. Negative times negative will become positive 1 over 1 negative x. Okay, now I have to simplify this one and solve for dy over dx, because dy over dx gives the differentiation of the given function with respect to x. Okay, so 1 over y times dy over dx equals to 1 over 2. Here, I have to add these two fractions. So here the denominators are different, and also the denominators contain variable. So I can use cross multiplication. That is, the 1 in the numerator of the first fraction has to be multiplied by the denominator of the second fraction, 1 negative x. The 1 in the numerator of the second fraction has to be multiplied by the denominator of the first fraction, 1 positive x. And then we have to multiply the two denominators. So I get 1 times 1 negative x positive 1 times 1 positive x over 1 positive x times 1 negative x. So 1 over y times dy over dx equals to 1 over 2 times. So I can distribute this 1 to this one and this one. I'll be getting 1 negative x positive 1. If I distribute this 1 to this one and this one, I'll be getting 1 positive x. So I can multiply this one and this one. So 1 times 1 is 1. 1 times negative x is negative x. X times 1 is x. And positive x times negative x will be negative x to the second power. So here negative x, positive x will cancel out. Here the same thing, negative x, positive x will cancel out. So I get 1 over y times dy over dx equals to 1 over 2 times 1 positive 1 will be 2 over 1 negative x square. Okay, here this 2 and 2 will cancel out. Okay, let's continue on the next page. Okay, this is a step I got it from the previous page. So because here this 2 and 2 are cancelled. So when I multiply this 1 and 1, it's just 1 in numerator. And when I multiply 1 and 1 negative x square, so the denominator is 1 negative x square. So I get 1 over 1 negative x square on the right side. Okay, here my aim is to solve for dy over dx. So I have to get rid of this 1 over y. So for that, I have to multiply both sides by y to get rid of the denominator y. So this y will cancel out. I get dy over dx on the left side, on the right side. So here we can replace this y by square root of 1 positive x or 1 negative x. So because this is the stuff which is equal to y. So here y can be replaced by, this y can be replaced by square root of 1 positive x over 1 negative x times 1 over 1 negative x square. Okay, I got the derivative of the given function, that is dy over dx is equal to square root of 1 positive x over 1 negative x times 1 over 1 negative x square.